A permutation is an arrangement of n number of objects in a definite order. And when I say definite order, what that means is that the order does matter. And that also means you can't have any repeats of any elements in that arrangement. And this is going to be important for us to distinguish when we look at combinations where order doesn't really matter, but we'll get to that in the next lesson. Now, an efficient way of finding the number of permutations is to use something called NPR, right? So N represents the number of elements that you have, right? And R represents however many that you are taking at a time. So R at a time. And all this N and R stuff will make a lot more sense when we actually see some specific problems in just a minute. But I want to make sure that I go over the structure of NPR first. So when we say NPR, what we're saying is we're going to look at n factorial over n minus r factorial. Okay, so n factorial over n minus r factorial. And I also want to talk about NPN real quick, and that's when the number of elements that you have is equal to the number of ways that you could take or elements that you're taking at a time. And that would just be NPN. And if we're familiar with factorial by now, we see that that would be n factorial over n minus n factorial, okay, which is also the same as just n factorial. And we'll see some problems with that in a bit. So I think a lot of this makes a lot more sense when we look at specific problems, so we can make sense of the formula and kind of what they mean. Otherwise, we're just kind of crunching numbers without any context. So let's look at this first problem. It says, how many ways can 10 children be arranged in a line? So imagine you have a group of 10 children and you need to put them in a line, right? So I want to kind of show out like what this means in terms of the arrangement first. And then I want to kind of show how we would do that just using the NPR formula, right? So first off, in the first spot, we have a group of 10 children that we can choose from. So we can put any one of those 10 children there. Now, once we have one of those 10 children in that spot, we can't then just clone that child and have another version of that child in the next spot. That would just be strange. So instead, we can now choose any one of the 9 remaining children. And after we've selected a student to go in that spot, then we've got a set of 8 remaining children to put there. And then so on and so forth. And if you see what I'm writing out here, this should look very familiar to you. This is exactly us just doing a factorial. This is equal to 10 factorial. And the quantity of this is going to be 3,628,800. So that's a lot of different ways that we can arrange these 10 children in a line, okay? Now, in terms of us using NPR as we've written, well, what are we effectively saying? This is equal to 10 P 10, right? What we're doing is we have a group of 10 children and we need to use all 10 children to form them in a line. So us doing it this way would be equivalent to us saying 10 factorial over 10 minus 10 factorial, which is 10 factorial over 0 factorial, which we remember by definition, we're saying that 0 factorial is equal to 1. And that's what should just give us 10 factorial. So now let's try a problem that has a little bit more specific conditions. So suppose you have a club and it has 30 members. How many ways can a president, a vice president, and a treasurer be chosen? So let's write this out. Again, I think writing out the different placeholders is helpful. So first off, how many different members are eligible to become president? So let me write that first. Okay, so for president, any one of the 30 members can be president. All right. Now, after we've chosen a president, we're going to assume that we're not allowed to then just have that same member also be vice president or treasurer. So what that means is in that next spot, we now have 29 eligible members to choose from to be vice president. And in that third spot, for treasurer, we're going to assume that we have 28 now. We now have 28 eligible members because there are 2 other members that have already been chosen to become either president or vice president. If we multiply all this together, we should get 24,360 different ways that we can choose these 3 officers from the 30. members that we have available. Now again, if we're looking this in terms of NPR, how would we set this up? We've got 30 members to choose from. That's our N value, P. And what is our R? We want to choose 3 positions or 3 officer positions from the 30 members that are available. So this would be 30P3. And to expand this out so we see what this looks like, this would be 30 factorial over 30 minus 3 factorial, which, and let me just make some space so I can finish writing all this, is equivalent to us saying 30 factorial over 27 factorial. And if you remember how this looks, that means we'd expand out the 30 factorial. This would be 30 times 29 times 28 times 27 factorial. And that's what we're able to divide out with that denominator. So we're left with 30 times 29 times 28, which is exactly what we're doing there. Okay? All right. Now we're getting a little bit more complicated in this next example. So I encourage you to pause the video and try to see if you can set this one up for yourself. A license plate has 2 letters and 2 numbers. How many plates are possible? Well, let me write out the 4 different spots where our letters and numbers are going to go. So we've got a couple of things that are unique about this problem. First, we have in the first spot here, let's just set this up to begin with 2 letters and 2 numbers. It doesn't say anything that we can't have any repeat letters. So we're going to say that we can choose from any 26 letters there, and we can then repeat that same letter if we need to. In other words, we could have like an A and an A there, for example. Now we have 2 numbers that follows in the next 2 spots. So we have 10 and 10. Again, we can have repeats of the same numbers. Now, here's the deal. Let me go ahead and highlight here what we're saying. This is a letter, this is a number, and this is a number. Nowhere in the problem does it say that the 2 letters have to be in front. So we have different arrangements here that we can work with. So let me first off write out how many different ways do we have for the current arrangement where we have 2 letters in the front and then 2 numbers in the back. We have 67,600 ways that are available here. Okay. The thing is, we have a number of different arrangements that we could have. So if you haven't already done so, I encourage you to think about and try to write out the different arrangements. We have number, number, letter, letter, number, letter, number, letter. And for alternating, we should be able to also have a letter, number, letter, number. Let's see, what else do I need? I need a number in the front, letters in the middle, and numbers in the back. And flip that around, letters in the front, numbers in the middle, and then a letter in the back. And I think I got them all. Pretty sure. So we should have a total of 6 different arrangements. So we're going to say, so let me just clear that up. There are 67,600 ways for each arrangement. And there are a total of 6 different arrangements that are possible. So if we multiply all this out, then what we have is a total of 405,600 license plates that are possible. I'm just going to underline that here. Okay. Now, if we wanted to come up with a number of arrangements fairly quickly, we wouldn't want to use NPR to come up with a number of ways that are available because it's not really a permutation. Notice, so what I'm saying here is we don't want to use NPR for this because the order didn't matter and we were allowed repeats. But we could use NPR to describe the number of different, or to figure out the number of different arrangements that we came up with. So there are 2 instances. Best way of thinking about this is there are 2 instances of a letter, and then there are 2 instances of a number. And so what we have is a total of 4 different things to choose from. There are 4 spots, so this would actually be 4 factorial over 2 factorial times 2 factorial. Or you can even think about it just as 2 minus 2 factorial, which would be equal to 6. So what I'm actually describing here is what's called a distinguishable permutation. So it's not exactly what we've done in the previous problems. This is what's called a distinguishable permutation, and is kind of our first example of this. And that's when we have a number of different r's to choose from. So in the previous examples, we had just one set of r's to choose from. Like in the previous problem, we said our r value was equal to 3 because we were choosing 3 officers from the 30 that we had available. In this problem, we were choosing 2 letters, but we're also choosing 2 numbers. So when we have a number of different r values that we are selecting from our group of n, r is going to represent the number of instances, I can't spell, the number of instances of one kind of object, okay? In which case we would say n factorial over, and for every r that we have, whether it's r sub 1, we would choose that r value factorial, okay? So I'm gonna actually go ahead and try these first 2 examples, the ones with the word cat and dad. What we're essentially trying to do is the number of permutations of each, and the permutations themselves of each word. And I'm going to do them kind of the traditional way, right? But I just want to also highlight kind of how we might do them using a distinguishable permutation. So let's start with the word cat. So what are the different permutations that we have of this word? In other words, pardon the pun. In other words, what are the different words that we can create using these same 3 letters? Well, we have cat, we have CTA, if we keep the C in the front the same. Then we move the A to the front, so we have ACT, ATC, TAC, and TCA. So we have a total of 6 here. So if we just chose NPR, we could say that this would be 3, pick 3. Oh, I should mention that saying 3P3, another way of saying that oftentimes when we're discussing permutations is to say pick. So 3 pick 3. So we would then say 3 factorial over 3 minus 3 factorial is equal to 3 factorial. Okay. Now, let's try this next example. What about the word dad? Now, this one's a bit different because 2 of the letters are the same. So what are the different permutations we can come up with here? This would be DAD, DDA, and ADD. And this would then be equivalent to, so we've got 3, obviously we have 3 different arrangements if I got them all. And so this would be equivalent to us saying 3 factorial over 2 factorial. Right? Or 3 pick, in this case, 1. Okay? So this would be equal to 6 over 2, which is just 3. Now, if we're thinking about this in terms of the distinguishable permutations, here's what's unique about this. And so let me go actually back to purple here so you can see how I would use the permutation for this one. So 3 factorial over 2 factorial, well, I'm choosing from 3. So this would be 3 factorial. But I've got one instance of the letter A, but how many instances do I have of the letter D? Well, 2 factorial there. So if I'm setting this up as a distinguishable permutation, then this is another way of exactly finding 3 as well. Let's go back to this first problem with the word cat. If I want to come up with the distinguishable permutations here, well, again, I'm choosing from 3 letters, but I've got one instance of the letter C, one instance of the letter A, and one instance of the letter T. So it's going to come out to the same thing. We're still going to get 6 here, but we're just setting it up a little bit differently. So let's try a little bit of a larger word now. Let's try the classic state, Mississippi. Go ahead and pause the video and see if you can come up with a number of distinguishable permutations of the letters in Mississippi. You don't have to write all the permutations out. Well, hopefully for this one, you counted up that there were 11 letters that were available to us total. and we had one instance of the letter M. Let me actually create more space. One instance of the letter M. We had four instances of the letter I, four instances of the letter S, and two instances of the letter P. So doing a distinguishable permutation that way, we should have ended up with 34,650 distinguishable permutations. Okay, so hopefully this helps give you a sense of, one, what a permutation is, how we can use NPR or NPICR to help come up with some permutations, understanding when to use it, and then also what to do when we have repeat instances of a certain R value, what we call distinguishable permutations.